December 1970. The Mediterranean Sea. The water is a slate of churning gray, agitated by the winter winds of the Atlantic approach. On the surface, the U.S. Saratoga, an aircraft carrier displacing 80,000 tons of American sovereignty, is conducting a full power run. In the high-stakes naval chessboard of the Cold War, the carrier was the queen. It was massive, heavily defended, and capable of 30 knots. At this speed, a carrier creates a wake that can be seen from space. The vibration of its 4 massive screws shuddering through the hull is a testament to brute mechanical force. The conventional wisdom of 1970 naval doctrine was absolute. No submarine could catch a carrier at full sprint. The mathematics simply didn't allow it. A submerged hull must push through water, a medium 800 times denser than air. The drag coefficient rises exponentially with speed. To overcome it requires energy that, at the time, existed only in theoretical papers, until the sonar operators on the Saratoga heard a sound that defied physics. Deep inside the Combat Information Center, amidst the glow of radar scopes and the hum of cooling fans, a headset crackled. Contact designated Sierra 1. Submerged. Closing from astern. The initial report was met with skepticism. A submarine closing from the rear meant it was traveling faster than the carrier. The sonarman checked his calculations. He checked the Doppler shift. He spoke into the comms loop with a voice that wavered between confusion and fear. Speed estimate 44 knots. Repeat, 44 knots. The captain of the Saratoga demanded a recount. He assumed the equipment was broken. Submarines did not move at 44 knots. The standard Soviet attack boat of the era, the November class or the diesel-electric Foxtrots, struggled to hit 25 knots, and they made enough noise doing it to be heard in the next hemisphere. To move a submerged steel hull at 44 knots would require an engine power density that existed only in science fiction. It would require overcoming hydrodynamic resistance so immense that the water itself would begin to boil around the propeller blades, a phenomenon known as cavitation. But the contact was real. It did not just catch the carrier, it overtook it. Sierra 1 circled the massive warship as if the American vessel were standing still. It danced around the Saratoga with an agility that suggested a total disregard for inertia. And then, with a burst of acceleration that registered as a screeching tear on the magnetic sonar tapes, it vanished into the deep. The vessel was K-162, Project 661. NATO would come to call it the Papa class. It was a titanium beast that held the world's speed record, a record that still stands to this day. When the reports reached the Pentagon, the initial reaction was panic, followed quickly by denial. Intelligence analysts offered a sliver of hope. They argued that K-162 was a unicorn, a single, ruinously expensive prototype that the Soviet economy could never afford to replicate. They believed the threat was an anomaly, a showpiece designed to frighten rather than a fleet designed to fight. They were wrong. Satellite reconnaissance over the secretive Severodvinsk shipyards soon revealed the terrifying truth. The Soviets weren't stopping with the prototype. High-altitude imagery showed new hulls on the slipways. They were smaller, sleeker, and more agile. They were building a production line, a new class of hunter-killers armed with the same titanium skin. It was Project 705, the Lyra, known to NATO simply as the Alpha. The Papa proved it was possible. The Alpha proved they were coming for us. To understand the magnitude of the Alpha crisis, we must first calibrate the baseline of 1960s anti-submarine warfare. The entire tactical doctrine of the United States Navy was predicated on the closing speed equation. In a hunter-killer scenario, the weapon, the torpedo, must possess a significant speed advantage over the target to account for maneuvering. The math is brutal. If a target moves at 25 knots, the torpedo must move at 40 knots to successfully intercept it before running out of fuel. For 2 decades, this equation favored NATO. The Soviet submarine fleet was composed largely of diesel-electric boats and first-generation nuclear vessels like the November class, which struggled to break 30 knots and generated immense noise while doing so. The primary U.S. weapon was the Mark 37 Mod 0. It was an electrically propelled, wire-guided cylinder with a top speed of 26 knots. Against a diesel boat moving at 6 knots, it was lethal. Against a November class moving at 28 knots, it was marginal. When the Alpha entered service, the equation collapsed. If a U.S. submarine fired a Mark 37 at a fleeing Alpha, the torpedo would not just fail to catch the target would actually pull away from the weapon. This was not a theoretical gap. It was a hard counter to the entire American order of battle. The Pentagon's war games revealed a catastrophic vulnerability. The Alpha was not designed for long patrols. It was an interceptor. Its mission profile was to sit in port, wait for a satellite cue indicating a U.S. carrier battle group, and then sprint into the Atlantic at speeds no Western vessel could match. Once in the battle space, the Alpha's agility was equally defying. Acoustic analysts noted that the vessel could accelerate from 6 knots to 40 knots in under 60 seconds. It possessed the thrust-to-weight ratio of a fighter aircraft. This acceleration allowed for a maneuver that American crews came to dread, the Crazy Ivan. A conventional submarine requires significant time and distance to turn. It banks slowly, fighting the resistance of the water, bleeding speed as it turns. The Alpha could execute a high G-bank, reversing its course in a radius so tight it defied hydrodynamic logic. In a close-quarters dogfight, this allowed the Alpha to check its baffles, the blind spot behind the screw, and fire a snapshot torpedo before the American submarine could bring its tubes to bear. The intelligence community was paralyzed. They were staring at a vessel that was half the displacement of a U.S. sub, yet twice as fast. It was as if the Soviets had taken a tank engine and mounted it inside a Ferrari. The question plaguing the Office of Naval Intelligence was simple. How? How could a nation that struggled to build reliable refrigerators produce a submarine that defied hydrodynamic drag? The answer lay in 2 decisions that Western engineers considered suicidal. The Soviets had abandoned steel, and they had abandoned water. This is not a story about who built the faster ship. It is an analysis of why the United States Navy looked at the most advanced piece of naval engineering on Earth and decided that the smartest move was to do nothing. But to understand that decision, we must appreciate the engineering marvel they were facing. Naval architecture is a war against weight. To make a submarine go faster, you need a larger reactor. A larger reactor requires a larger hull to provide buoyancy. A larger hull creates more surface area, which creates more drag. More drag requires an even larger reactor to overcome it. This is the spiral of diminishing returns. It limits conventional submarine speeds to roughly 30 knots. To break this cycle, the Soviet Malachit Bureau realized they needed to fundamentally alter the density of the vessel. They needed a material that was lighter than steel, but strong enough to withstand the pressure of the deep ocean. They chose titanium. Titanium is the holy grail of structural engineering. It is 40% stronger than steel for the same weight. It is non-magnetic, drastically reducing the vessel signature on the magnetic anomaly detectors used by American patrol aircraft. And it is impervious to corrosion. A titanium hull would last forever in salt water. But there is a reason the U.S. Navy did not use it. Titanium is a metallurgical nightmare. At standard temperatures, it is a benign silver-gray metal. But at welding temperatures, the point where the metal liquefies to join 2 plates together, titanium becomes a chemical sponge. It possesses a violent affinity for oxygen, nitrogen, and hydrogen. If a welder attempts to join 2 plates of titanium in an open shipyard environment, the metal will absorb these atmospheric gases instantly. The result is hydrogen embrittlement. The weld might look perfect to the naked eye, but at a molecular level, the metal lattice has been compromised. It loses its ductility. It becomes as brittle as glass. Under the crushing pressure of a deep dive where the ocean exerts tons of force on every square inch of the hull, the metal wouldn't bend or groan. It would shatter. To build the Alpha, the Soviet Union had to attempt the impossible. They had to construct the largest hermetically sealed environments on Earth. Severodvinsk Shipyard. Building number 42. Status: restricted. Atmosphere: argon. Building 42 was a cathedral of inert gas. The entire assembly hall was purged of air and flooded with high-purity argon. Argon is a noble gas. It does not react with titanium. But humans cannot breathe argon. The workers inside Building 42 could not breathe the air they stood in. They were encased in pressurized suits resembling cosmonauts, tethered to external oxygen supplies by long rubber hoses. They moved like deep-sea divers, welding the hull sections of the Project 705 in an alien atmosphere. The complexity of this process was staggering. A single microscopic leak in a welder's suit meant death. A single impurity in the argon mix meant the hull section had to be scrapped. The rejection rate was astronomical. The cost was ruinous. The titanium sponge required for the fleet was so expensive, and the manufacturing process so laborious, that the predecessor class, the Papa, earned a cynical nickname within the Soviet Admiralty, the Golden Fish. They joked that it would have been cheaper to construct the hull from solid gold, but the result was undeniable. The Alpha displaced only 2,300 tons surfaced. This was less than half the weight of the American Los Angeles class. With a hull capable of diving to depths the West could only estimate, depths where American torpedoes would be crushed by pressure before they could even detonate, the Alpha could operate in a thermal layer of the ocean that was effectively a sanctuary. But a light hull was only half the equation. To achieve 40 knots, the Alpha needed an engine with power density that exceeded anything in the Western inventory. They needed a reactor that ran hotter, faster, and more aggressively than physics should allow. They needed liquid metal. Every nuclear reactor in the U.S. Navy, from the Nautilus to the modern Virginia class, is a pressurized water reactor, or PWR. The concept is simple. You split uranium atoms to generate heat. You pump water through the core to absorb that heat. You use that hot water to boil a secondary loop of water into steam, which spins a turbine. Water is safe, but as a coolant, water has two significant limitations. First, it is a poor conductor of heat compared to metal. Second, it boils at 100 degrees Celsius. To prevent the water in a reactor from turning into steam inside the core, it must be kept under immense pressure, over 2,000 pounds per square inch. This necessitates heavy, thick-walled piping and massive pressure vessels. A PWR is inherently heavy. The Soviet engineers calculated that a water reactor would never fit inside the 2,300-ton displacement limit of the Alpha. They needed a coolant that could absorb heat 10 times faster than water, without the need for heavy pressurization. Their solution was the OK-550 reactor. The coolant was not water. It was a molten alloy of lead and bismuth. The physics of lead-bismuth eutectic, or Welby, are seductive. Lead-Bismuth has a boiling point of 1,670 degrees Celsius. This meant the reactor could operate at extremely high temperatures without the coolant flashing into steam. Consequently, the primary loop did not need to be highly pressurized. The heavy steel piping required for a U.S. reactor could be replaced with thinner, lighter components. More importantly, molten metal moves heat with terrifying efficiency. In the Alpha's Lead-Bismuth core, the thermal conductivity was so high that the reactor effectively had no thermal lag. The captain could order full power, and the reactor would respond instantly. This was the secret to the Alpha's acceleration. It could go from idle to full thrust in the time it took a U.S. submarine to verify the order. Combined with the titanium hull, the LB reactor gave the Alpha a power-to-weight ratio that was unmatched in maritime history. It was a technological triumph. It was the future of naval warfare. Or so it seemed. But in their pursuit of the perfect thermodynamic cycle, the Soviet designers had overlooked a critical operational flaw. A flaw that would not show up in the equations of a physics textbook, but would reveal itself in the brutal reality of the Arctic winter. The fatal flaw of the Alpha class did not lie in its titanium skin or its hydrodynamic profile. It lay in the very heart of its propulsion system. The Soviet engineers had achieved a miracle of thermodynamics with the Lead-Bismuth eutectic reactor, but in doing so, they had entered a Faustian bargain with physics. Water, the universal coolant of Western reactors, has a forgiving nature. When a water-cooled reactor is shut down, the water simply cools. It remains a liquid. It flows. It can be pumped, drained, or replenished. It is chemically stable. Lead-Bismuth is different. It is a metal that mimics water only when hot. Above 125 degrees Celsius, it is a fluid silver stream, carrying heat with incredible efficiency. But below 125 degrees Celsius, a temperature barely higher than boiling water, the physics of the eutectic alloy take over. The liquid metal undergoes a phase change. It turns into rock. This physical constant created a logistical nightmare that would haunt the Soviet Northern Fleet for the entirety of the Cold War. To keep the Lead-Bismuth molten, the Alpha's reactor could never be turned off. Even when docked in port, even when the crew was on leave, even during routine maintenance, the reactor had to run. It had to generate enough decay heat to keep the coolant loops above the freezing threshold. This requirement effectively tethered the supersub to the pier. The Alpha was not an independent warship, it was an invalid plugged into life support. When the reactor had to be shut down for refueling or major repairs, the submarine was dependent on external heating. Superheated steam from the naval base's power plant had to be pumped constantly into the submarine's heat exchangers to keep the metal liquid. If that shore steam failed, and in the remote, frozen, crumbling infrastructure of the Soviet naval bases in the Arctic Circle, infrastructure failure was not a possibility. It was a probability. The submarine would die. The fragility of the Project 705 design was not hypothetical. It was demonstrated with devastating finality aboard the lead ship of the class, K-64. In 1972, shortly after commissioning, K-64 was preparing for deployment when disaster struck. A leak developed in the primary cooling loop. As the pressurized liquid metal escaped, the level in the reactor vessel dropped. The circulation pumps lost suction. The flow stopped. The crew watched their gauges in horror. Without the constant circulation of heat, the temperature in the core began to plummet. They raced to connect auxiliary heating systems, but the laws of thermodynamics were faster. As the temperature gauge fell past 125 degrees, the liquid metal inside the reactor core froze. In a matter of hours, the heart of the submarine transformed into a solid, immovable block of radioactive metal. The fuel rods were encased in lead. The control rods, essential for regulating the nuclear reaction, were seized in place. There was no way to thaw it without melting the reactor vessel itself. There was no way to chip it out. The reactor was effectively a monolithic tomb. The Soviet Navy towed the brand-new billion-ruble vessel back to Severodvinsk. The damage was terminal. They sawed the bow off for use in training simulators and towed the reactor compartment out to the desolate waters of the Kara Sea to scuttle it. The most advanced submarine on Earth had been defeated, not by an American torpedo, but by a drop in temperature. This disaster was not an isolated incident, it was a prelude. The requirement to keep the ships hot at all times overwhelmed the fragile Soviet infrastructure. Shore steam lines would freeze and burst in the bitter Arctic winter, forcing crews to run the reactors dangerously hard while docked, just to keep the coolant liquid. Then came the catastrophe on K-123. During a routine patrol, a leak erupted in the steam generator. Radioactive coolant entered the reactor compartment. The alarm klaxon screamed, all hands mask up. But this was not a steam leak. It was a metal leak. 2 tons of molten Lead-Bismuth, glowing with heat and radiation, sprayed into the engineering spaces. It didn't just irradiate the compartment, it acted like liquid lava. As it hit the cold steel decks and the complex machinery, It cooled and solidified instantly. It welded valves shut. It encased electrical panels in heavy metal. It entombed the compartment in a toxic radioactive shell. The crew survived, but the ship was ruined. The cleanup took 10 years. The hull had to be cut open, the reactor compartment cut out, and a new one installed. The Alpha was proving a harsh truth with every accident. It was a Formula One car trying to survive in a demolition derby. It was fast, it was exotic, but it was too fragile for the brutality of war. In Washington, the specifications of the Alpha were laid before the one man who held the power to alter the course of the U.S. Navy, Admiral Hyman G. Rickover. Rickover was not merely an officer, he was an institution. As the director of naval reactors, he served for over 30 years, surviving presidents and secretaries of defense who tried to fire him. He was a man of legendary, abrasive intellect. Small, frail-looking, and famously intolerant of mediocrity, he held absolute authority over every aspect of American nuclear propulsion. He was the gatekeeper. No bolt, no valve, no officer went onto a nuclear submarine without his personal approval. The panic in the Pentagon was palpable. The generals and the defense contractors were pushing for a symmetric response. The logic was linear. The Soviets have a 40-knot titanium sub. We need a 45-knot titanium sub. We need to close the kinematic gap. The blueprints were already being drawn up for American liquid metal fast-attack boats. They promised speeds that would rival the Alpha. They promised to match the Soviets' innovation for innovation. Rickover looked at the intelligence. He studied the reports on the Lead-Bismuth reactor and the titanium welding, and he famously demurred. He did not order a crash program to copy the Alpha. Instead, he validated a completely different approach. Rickover knew something the Soviet designers were about to learn the hard way. The U.S. Navy had already built a liquid metal submarine. In 1957, the US Seawolf, the second nuclear submarine in history, was launched with a sodium-cooled reactor. It was designed for the exact same reasons as the Alpha: higher thermal efficiency and greater power density. It was a disaster. The logbooks of the Seawolf tell a story of constant peril. Sodium leak detected in steam generator loop. Coolant activity critical. Sodium is highly reactive. When it leaks and contacts water, it doesn't just contaminate, it explodes. The Seawolf was plagued by superheater leaks and corrosion issues that kept the vessel constantly on the verge of a catastrophic thermal event. In 1958, Rickover ordered the sodium reactor cut out of the hull and replaced with a standard pressurized water reactor. His verdict was absolute. Reactive coolants have no place in a warship. Rickover understood the fundamental difference between a laboratory and a battlefield. A combat vessel is not a controlled experiment. It is a home for 100 men operating in a hostile environment, submerged for months at a time, thousands of miles from support. Complexity is the enemy of survivability. He identified the Alpha's Achilles heel immediately: the Port Queen problem. Rickover's doctrine was clear. The goal of the American Navy was global power projection. A submarine that requires a team of PhD physicists and a dedicated steam plant just to sit at the dock is useless in a global conflict. He championed a philosophy of soft specification. While the Soviet Malakit Bureau pursued hard specification, maximum speed, maximum depth, maximum automation, Rickover prioritized reliability, acoustic stealth, and logistics. He believed that a weapon system's effectiveness is determined not by its peak performance in a sea trial, but by its sustained availability in a theater of war. He asked a simple question: what good is a 40-knot submarine if it is frozen to the pier in Murmansk? However, the tactical problem remained. The Alpha was still out there. When it did work, it was still faster than any torpedo in the U.S. inventory. Reliability wouldn't matter if the American subs were destroyed before the fight began. The U.S. Navy needed a solution that didn't involve exotic metals or dangerous coolants. They needed a way to kill a 40-knot target with a 25-knot platform. The answer lay in a new doctrine: asymmetric warfare. If you cannot outrun the enemy, you must ensure he never sees you. And if he does see you, you must have a weapon that doesn't just chase him, but outsmarts him. The American response to the Alpha was to double down on the Los Angeles-class submarine. Compared to the titanium-skinned, liquid metal-powered Alpha, the Los Angeles, or 688, was boring. It was built of high-tensile, high-80 steel, not titanium. It used a standard S6G pressurized water reactor, not liquid metal. Its top speed was classified as 30-plus knots, fast, but technically slower than the Soviet sprint speed. To the casual observer, it looked like the Americans had brought a family sedan to a drag race. But the Los Angeles possessed the one attribute that the Alpha lacked. It possessed the one thing that matters most in underwater warfare: silence. The Alpha was fast, but it was deafening. The flow noise of water rushing over the hull at 40 knots was immense. Worse, the pumps required to circulate the heavy Lead-Bismuth coolant created a distinct mechanical resonance that carried for miles. At high speeds, the Alpha lit up passive sonar screens across the entire North Atlantic. It was a screamer. The Los Angeles class was designed to be a hole in the water. Its machinery was raft-mounted, suspended on rubber isolation mounts to prevent vibration from transferring to the hull. Its skin was coated in anechoic tiles, rubberized mats that absorbed sonar pings rather than reflecting them. A 688 patrolling at 5 knots was virtually undetectable against the background noise of the ocean. The U.S. doctrine shifted to first look, first shot, first kill. The plan was not to chase the Alpha. The plan was to ambush it. But an ambush requires a weapon that can finish the job. The Mark 37 torpedo, with its 26-knot speed, was retired. In its place, the Navy deployed the Mark 48. The Mark 48 was the true Alpha killer. It was a heavyweight monster. Unlike the battery-powered electric torpedoes of the past, the Mark 48 used a swash-plate piston engine fueled by Otto Fuel II. This was a combustion engine that could breathe underwater, carrying its own oxidant. It allowed the weapon to scream through the water at 55 knots, deep enough and fast enough to run down the titanium fugitive. Throughout the 1980s, this capability was refined into the ADCAP, Advanced Capability. Engineers hardened the guidance wire and rewrote the logic software to specifically counter the Alpha's agility. The ADCAP didn't just home in on sound, it anticipated maneuvering. If an Alpha attempted a high G-Crazy Ivan turn, the ADCAP's digital brain would recognize the geometry. It would not try to turn inside the sub, it would calculate an intercept point. The math had been corrected. Even if the Alpha ran at 42 knots, the Mark 48 ADCAP closed the distance at a relative speed of over 10 knots. More importantly, the acoustic disparity meant the engagement would never be fair. Because the Alpha was so loud, it would be detected at 50 miles. The silent Los Angeles could approach to within 15 miles before firing. The Soviet pilot would be dead before he ever saw the American submarine. The Alpha was a blind sprinter running into a sniper's sights. The Cold War underwater arms race is a definitive case study in the tension between theoretical performance and operational reality. The Soviet Union built 7 Alpha-class submarines. They were technological marvels, pushing the boundaries of metallurgy and thermodynamics to the absolute edge. But they were strategic failures. They spent the vast majority of their service lives tied to the pier, broken by the complexity of their own systems. The stress of maintaining the liquid metal reactors drained the Soviet naval budget and demoralized their crews. They were a weapon that worked perfectly on paper, but failed in the water. The United States built 62 Los Angeles-class submarines. They were conservative, reliable, and mass-producible. They became the backbone of Western naval dominance for 40 years. They could deploy anywhere, anytime, without the need for specialized support fleets. The legacy of the Alpha is a lesson for every engineer and strategist. It is tempting to chase the apex of performance, to use the most exotic materials, the highest temperatures, and the most radical designs. It is tempting to believe that superior specs equal superior capability. But war is not won by the device that has the highest numbers on a spec sheet. It is won by the device that shows up. The U.S. Navy won the underwater Cold War not by being faster, but by being smarter. They realized that in the unforgiving, crushing darkness of the deep ocean, the most powerful capability of all is reliability. Sometimes, the most advanced move is simply to build a machine that works. This is apex engineering.